Today, I'm going to present our work titled FLARES, Fast and Accurate LiDAR Multi-Range Semantic Segmentation. This work is done jointly by Robert Bosch and the University of Lübeck. The work focuses on improving both accuracy and efficiency for LiDAR semantic segmentation. LiDAR semantic segmentation is a fundamental perception task in autonomous driving. It assigns a semantic label to each 3D point, enabling fine-grained understanding of the surrounding environment. However, LiDAR point clouds are sparse, irregular, and large-scale, which makes efficient and accurate segmentation particularly challenging. To address efficiency issues, many recent methods project point clouds into range view images. This representation allows us to leverage mature 2D convolutional or transformer-based networks. This significantly improves inference speed compared to 3D point or voxel-based methods. However, range view projection introduces a critical limitation known as the many-to-one problem. Specifically, multiple 3D points are projected onto the same pixel, and only the closest one is preserved. This leads to irreversible information loss. A common workaround is to increase the azimuth resolution of range images, but this results in a very wide panoramic images, which are inefficient to process. To address the aforementioned issues, we propose FLARES, a new training and inference paradigm for multi-range LiDAR semantic segmentation. Instead of processing a single panoramic range image, FLARES first split the input point cloud into multiple subclouds homogeneously for subsampling. Each subcloud is then projected into a thinner range image. During training, we randomly sample one of these range images to form a training input. During inference, all range images are concatenated into a batch and processed in parallel. Finally, we apply a dedicated post-processing step to fuse the predictions and recover the full point-wise semantic labeling of the original point cloud. This design allows us to improve segmentation accuracy by reducing projection field conflicts, since point cloud splitting provides more projection space for each subcloud while still maintaining high computational efficiency. Moreover, FLARES is model agnostic. It does not require any architectural modifications and can be directly applied on top of existing range view segmentation networks. However, splitting the point cloud into multiple ranges introduces several new challenges, which we will analyze next. First, point cloud splitting exacerbates class imbalance. Rare classes may appear only in a few subclouds, making learning unstable. Second, projecting subclouds amplifies noise and distorts object boundaries in the range image, especially in regions near split borders. Third, existing post-processing methods require iterative fusion across all range images, which significantly slows down inference and undermines efficiency. These challenges indicate that multi-range semantic segmentation requires specialized training strategies and post-processing, rather than naively extending single-range image pipelines. To address class imbalance, we introduce weighted page job plus, so-called WPD+. Unlike previous methods that operate on 2D range images, WPD+ works directly in 3D space. It selectively pastes underrepresented objects while suppressing dominant classes to improve long-tail performance. To further enhance real classes, we additionally paste objects from a synthetic dataset generated from a simulator. Despite the domain gap, this synthetic data proves highly effective for improving segmentation accuracy of small and dynamic objects that has significantly lower occurrence in real-world datasets. Next, to address projection noise, we propose multi-cloud fusion. For a given range image, we fill unoccupied pixels using information from the other subclouds at the same pixel location. As shown here, MCF significantly increases pixel occupancy and reduces projection artifacts. After network prediction, We need to reproject 2D results back into 3D space. Standard KNN-based methods are computationally expensive and inefficient in the multi-range setting. We therefore propose a new post-processing algorithm called nearest neighbors range interpolation, or NNRI. Instead of searching neighbors in 3D space, NNRI first uses a fixed 2D kernel to collect nearest neighbors directly in the range image. This step is highly efficient and avoids expensive 3D neighbor search. Next, we compute the relative depth distance between each 3D point and its 2D neighbors. This allows us to reason about geometric consistency using depth information. We then apply an adaptive cutoff threshold, which depends on the point distance to the sensors. Nearby points use a smaller threshold, while distant points use a larger one. Finally, we interpolate softmax scores instead of hard labels, resulting in more accurate and stable predictions. We evaluate flares on two large-scale benchmarks, Semantic Kitty, which contains dense 64-beam LiDAR scans, and NewScenes, which is sparser and more challenging with 32-beam LiDAR. Across different architectures and two datasets, flares consistently improves performance. We observe significant gains in segmentation accuracy, particularly for small and underrepresented class, while maintaining strong computational efficiency. Our ablation study shows that each component contributes to the final performance. In particular, combining flares with all the components in our proposal leads to the best trade-off between accuracy and efficiency. Specifically, we gain 45% inference speedup and a 4.4 MILU improvement compared to the baseline. This demonstrates that flares is an effective and scalable training paradigm for range-field LiDAR semantic segmentation. We would also like to show some qualitative results from our methods. Thank you for watching.